Hello, everyone, from another side of the globe and another time zone. I'm Tatiana, co-organizer of the VISION workshop this year, and today I want to tell you a bit about statistics on the paper review process we had this year. So this year we had again 2 tracks with regular paper and extended abstract. For extended abstract, we only had 7 submissions, while for the regular paper, we had 36 papers with larger work for reviewers to do this year. So in summary, we have submissions from 16 countries, 43 universities, and 10 companies. Thanks to Shen Kong, you can see now the most frequent words appearing in the papers, which is not surprising having the topic of the workshop, of course, but some interesting words appear here, so you could find corrosion, polyp, and cost. This year, we had an amazing pool of reviewers without whom workshop could not happen. So thank you so much for all your hard work, for all the help, and also being flexible with the timelines. Based on the reviews and meta-reviews, we have selected 5 papers for the oral presentation. These papers will follow after my slides. And one of these papers we selected for the Best Paper Award. And with that, the Best Paper Award goes to an augmentation-based model readaptation framework for robust image segmentation, authored by Jaming, Joseph, Jonathan, and Boguslav. Sorry for my errors in name pronunciation. This happens often with me. So this paper addresses 2 key challenges. The first one is the small dataset size at the start of production. And the second one is continuous dataset drift due to changing measurement conditions. The method overall aims to adapt the model to these changes by adaptively selecting augmentation operations and applying them to the current training set. The paper in a nutshell has a simple method while being effective and considers real industrial application. With that, congrats authors on the amazing work and congrats on the award. With that, we all go now to the oral talks. Thank you.
Start again. Hi everyone, my name is Joe. It's a great pleasure to introduce our paper, an augmentation-based model readaptation framework for robust image segmentation. I'm the second author on the paper and a PhD student at Newcastle University in the UK. Jaming, the main author, would have loved to come, but unfortunately due to travel restrictions, he wasn't able to. So the main motivation of our work is, suppose you have a model trained on a data set given to you with full annotations and masks, like you can sort of see in the sort of pinkish colored data set with the colored masks over the images. But then later in the timeline, multiple data sets become available that are similar, but are missing the masks. How can you use that same model on those images and readapt it for them? So in these new data sets, DT2 and DT3, they face a high degree of disparity surrounding the region of interest, which is the ACF code on the middle image there. They're very similar, but they have lots of differences between, lots of issues with the images, such as a changing distance between the object and the camera, some bumpy textures formed by plastic molding, and then other natural noises in the images, like stains, or some of the images still have the film over the image of the picture of the shampoo bottle before it was taken. With these challenges and industrial inspection context, we aim to fine-tune a line-weight model that, with the least effort, that is competitive to a large-scale pre-trained model like SAM in segmentation and cropping. On top of that, we also use these cropped images in a classification network. So we want to maximize that optimization as well, that gives us best classification accuracy. To do this, we propose an augmentation-based model readaptation framework to achieve our goals. Some of the details from this slide have been omitted to try and make you read the paper for the full details or look at the poster over there. With these challenges, the main idea is we fine-tune the existing model with the original data. We then have an evolving augmentation pool where candidate augmentation methods and their values are tested out on images that were unsuccessfully segmented by the original model. And then based on how these segmentation methods and the values work. If they're strong and improve the model's accuracy, they're then reintroduced to the original model, and we start again and keep going in the loop until we have a sort of finite, perfect, smallest set of augmentation methods that achieve the highest accuracy in segmentation and classification. So just looking at some of the performance here, we've summarized all the cropping and subsequent classification performances over the two data sets, DT2 and DT3 in these two figures. DT2 being the figure on the left and DT3 being the figure on the right. And the classification accuracy was reported by pre-trained ACF classification models released in a previous publication of ours. And the radius of these circles shows the number of hyperparameters for these models. And as you can see, the accuracy goes up. Sorry, the accuracy of these models goes up. But they are like fine-tuned models with smaller augmentation sets, while also having a lot less hyperparameters, making them more applicable for like mobile phone applications. We also had two stages of our experiments. The first one being to find the optimal scaling range, and the second was determining the optimal evolving augmentation ball that I mentioned before. So here we've visualized how these methods have improved the model's ability to segment the problem images. So there's examples there of reduced stains and bumps and things like that, where before where the boxes of red outline, that's where the model before wasn't able to crop the image, whereas the blue outline shows successful cropping. And with our small set of optimal augmentation balls, you can see on the very rightmost column that it was able to segment the images correctly. So sort of summing up, and in conclusion, we proposed an automatic augmentation method determination framework for training. We proved the feasibility and efficacy of the proposed framework on two convolutional segmentation networks in surpassing the pre-trained SAM. And we showed that performing pseudo-readaptation could be a feasible starting point for fine-tuning a lightweight segmentation network for deploying the proposed framework in a diverse industrial scenario, where merely the model with the smallest amount of weights learned from the earliest data release is required to manage the core growth. So thank you for all listening. I'd point some of the questions towards Jolene, since he's the original author, but that's the information. Thank you.
So like you mentioned, I want to give the last award certificate. Thank you very much. Okay, now let's move to the second oral presentation.
Now I will present our work for the different names for scalar quantized representation learning for unsupervised multiplication and localization. Let's summarize our work. Let's start by looking at the problem. Traditional autoencoder faces some challenges. For example, it's overgeneralized, means that they directly copy features or fail to reconstruct image accurately, making anomaly appear normal. Our solution has three main components. First, we use multiple synthetic anomalies to diversify our training data. Second, we implement the vector quantized-based autoencoder for better anomaly detection. Lately, we apply a finite scalar quantization to prevent corpus collapse. And we also test 5 data sets, including a VTech and the VSA, and then get very good results. Okay. Here is our we will propose the related work and our mission and its implemental results in the conclusion. Traditional autoencoder often face failure cases in anonymization. One of the biggest problems is overgeneralization. In some cases, here you can see the model may directly copy or poorly reconstruct with wrong samples, which reduce its effectiveness detecting real anomalies. Later, I will show our models learn more robust, maybe between image and the latent encodings avoid these pitfalls. Here is our method. Let's talk about post method. The core is a scalar quantized autoencoder. Synthesis images are first passed through an CNN-based encoder, where they are quantized and then encoded to generate reconstruct images. To optimize this process, we use electrons and structure similarity. During training, we also incorporate the micro-synthetic data generation strategy to combine 4 different methods to create diverse synthetic anomalies, helping the model more robust. The architecture includes a dual complex encoder platform and the dual encoder design intensity solely for accuracy for anomaly localization. Here, our has been tested on 5 well-known data sets, including NVTech and VIS and others. This slide shows what type of synthetic images we use to enhance the robustness of our model. Okay, let's compare the original reconstruction encoder with our model. Traditional autoencoder often overgeneralize, particularly with structure informed sample, which make detecting anomalies more difficult. They also tend to rely in irrelevant features like background, color, and lighting, which negatively affect image reconstruction quality. In contrast, our VQ-based score model with its compression reconstruction framework filters out this noisy information and focus on the essential features for recognition. It's made more accurate to discrete data encodings about the common issue of overgeneralization. Here, you also can see some qualitative results. As you can see, our model is able to reconstruct the normal image and accurately highlight the anonymous region, which is critical for both detection and the localization tasks. Okay, in conclusion, our scored model effectively tackled the key challenges autoencoder face in some the anomaly detection, particularly the direct copy issue, often seen in the construction-based model. By replacing the vanilla vector quantization with finite scalar compilation and utilize multiple synthesis methods, we significantly enhance the precision of anomaly localization and segmentation. Our model outperformed across 5 data sets and offer a more cost-effective solution for industrial anomaly detection compared to diffusion model. Thank you very much. Thank you, everyone.
Okay, thanks for the presentation. Let's go quickly to the third one. So the third, you prefer this one? This microphone is good for, you know?
Yes, I think. Can you hear me? That's okay. So, hello, my name is Pantelis Medesidis, and I work for University at Thessaloniki as a research assistant. And I will present you the foreground-aware knowledge distillation for enhanced damage detection. So, automated drone-based inspection with artificial intelligence can improve safety and efficiency in industries like inspection on power lines and inspection on insulated pipes. Early detection on pipe damages prevent leaks, ensuring operational effectiveness and environmental sustainability. Advanced DNN models often struggle on real-world application, such as outdoor industrial environment, like the PDI dataset images, because they are typically cluttered and noisy. So significant challenges under these harsh conditions can appear. Knowledge of pipe regions can improve performance of the detection model. For example, if we know the pipe region, we can remove the background, or we can blur the background, or even we can enhance the foreground and help the detector. But obtaining pipe regions during inference is not trivial because we will create a slower system performance and potential errors may be propagated from the segmentation model. So we propose a model agnostic knowledge distillation framework that utilize the foreground knowledge of the pipeline mass only at the training phase. And we enhance vision-based damage detection in clutter environment. Here we can see the architecture overview. Let me explain a little bit. We have two identical models, the teacher and the student. The teacher is pre-trained with pre-processed images, for example, the images without background. And at the student's training phase, the student receives the original RGB images while the teacher receives the pre-processed images. And we have a knowledge distillation loss between the features of the two models. So for our results, we improve the performance almost in every state-of-the-art detection model, like YOLO V5, YOLO V6, YOLO V8, and even in transformer-based architecture, like RTData. So to conclude, we propose a model agnostic knowledge distillation approach that utilize the foreground knowledge, and we increase the mean average precision of the state-of-the-art detector at PDI dataset at 12%. Thank you very much for your attention.
Hello, everyone. I'm Ying from RICO Software Research Center, Beijing. Today, I would like to share our recent research, Anomaly Factory. Regard anomaly generation as unsupervised anomaly localization. Recent advances in anomaly generation approaches alleviate the effect of data insufficiency on task of anomaly localization. While effective, most of them learn multiple, large generative models on different datasets and cumbersome anomaly prediction models for different classes. To address the limitations, we propose a novel scalable framework named Anomaly Factory that unifies unsupervised anomaly generation and localization with same network architecture. Unlike prior art, it learns only 2 generators and 1 predictor with same network architecture to solve tasks on M classes of N datasets. Our aim is to build a unified network architecture that works for anomaly generation and anomaly localization. Essentially, these 2 tasks both can be defined as the formulation, where the output image is a fusion of the input image and the generated texture image with the guidance of a heat map. To train the network only with normal samples from 5 datasets, we introduce a progressive pipeline that consecutively learns a boot generator, a flare generator, and a blaze detector. The boot generator receives a target edge map and a reference color image having different augmentations, and generates an image combining the structure and appearance of them. It triggers the generation ability of absorbing structure of a target edge map and appearance of a reference color image. The flare generator receives manipulated edge maps and supervision signals from the boot generator. It generates anomaly images accompanied with anomaly heat maps that accurately indicate pixel-level anomaly locations. Compared to boot generator, flare generator can generate high-quality anomaly image even if the target edge map is drastically manipulated. Different with existing methods, our method generates multiplicate normal samples cross different domains, both photorealistic logical and structural anomalies, and accurate anomaly heat maps. We achieve competitive diversity and use only one generative GAN-based model that works for 5 datasets and is scalable for handling more categories. By simply swapping normal images with the generated anomaly, we train the Blaze detector. It directly produces high-quality anomaly heat maps by learning anomaly images generated by the flare generator. This paper proposes a novel scalable framework that unifies unsupervised anomaly generation and anomaly localization. It generates realistic and diversity anomalies, and simultaneously produces accurate anomaly heat map. Extensive experiments carried on 82 object categories of 5 datasets demonstrate the superiority of Anomaly Factory over the existing anomaly generators for anomaly localization task. Please refer to the paper for more details. Thank you for watching.
Hi everyone, I'm Mohammad Akil and today I'm going to present my paper Meta-Learning Driven Iterative Refinement for Anomaly Detection in Industrial Inspection. In modern industrial setting, anomaly detection plays a pivotal role in ensuring quality control. Traditional event analysis methods work effectively in some cases but often fail in complex settings. While deep learning methods perform powerful, but they require a large amount of label data to train them. So the objective of our work is to develop a robust anomaly. It is not moving the side. Yeah. So the objective of our work is to develop a robust anomaly detection framework which can overcome these problems and which can perform well in noisy data environments. So we propose a meta-learning driven iterative refinement. Meta-learning allows model to adapt to new tasks using minimal data, making it ideal for industrial application where label data is scarce. Our framework also incorporates iterative refinement, which continuously improve the model by recalibrating the data during training. The key innovation could be a dynamic threshold. Our model throughout the training, it can automatically set the threshold and remove the data points which are above that threshold. So let's move to meta-learning optimization process. Meta-learning consists of 2 key loops, the inner loop and outer loop. In inner loop, as shown in previous diagram, we initialize the model with random parameters. It then processes a batch of data, adapt to it, and update the gradient descent. And it repeats for the whole data set. And after when data is completed, it updates the meta parameter, which is called the outer loop. For our experiment, we use 2 state-of-the-art dataset. One is METech-AD and the other one KSCD2 dataset. And we use noise levels from 0 to 50%. We use the different net as our baseline model. As you can see, the model performed better throughout the model performed throughout the noise levels from 0 to 50%. But the key point is that at 0%, we increase the performance up to 3%. It is because our model successfully increased the false negative and reduced the false positive. So we get a better results at 0 level than the baseline model. So let's conclude. In conclusion, we develop a meta-learning driven iterative framework that improves the anomaly detection framework performance, particularly in noisy environments. However, our approach has limitations such as the potential for overfitting or underfitting because it is automatically removing the data points that could be due to underfitting or overfitting. It can remove the good data points. So, in future, we would like to explore the adaptive algorithms and regularization to counter this problem. Thank you so much. If you would interested, we can talk at poster session. That's it. You can. Thank you so much.